Now the RPM sensors that we used, we had a lot of trouble with these. We first used magnetic Hall effect sensors. Now these were very cheap, but very unreliable for us. If they output a signal at all, they output a very noisy analog signal, and we figured that massive amounts of signal processing was not relevant to our project. So we moved on to the optical sensors. Now these also were cheap, but output a strong digital signal. They were useful in this sense, but they were unreliable. They actually required us to hold a flashlight above the sensor, which was unfeasible as it's mobile. We didn't want to stand there running after the car. We replaced these with off-the-shelf IR encoders. These IR encoders had their own wheel encoder and their own digital encoder. Now these were both reliable and output a very distinct digital signal that we used for determining the RPM of each wheel individually.
We needed a test platform for our design. We first decided to try Legos. This seemed to be an easy way to implement it and also inexpensive, considering one of us had a great supply of them. We found this to have trouble bearing the weight of all of our components, and we decided to move on to a different medium for building our chassis. Our second generation was angled aluminum. This was strong, a little heavier, and it had inherent mechanical problems since we were electrical engineers. It turned out that due to friction, our steering servo wasn't strong enough to reliably move the steering angle of our car. We borrowed an RC control from a Radio Shack car that you'd buy your 5-year-old. This worked well to power and move the servo, also acted as a start and stop for our program. To test our design, we conducted 3 trials. Each trial varied between 0 and 30 degrees in 1 degree increments. In order to see the difference between the inner and outer wheels, we captured the wave output from the wheel encoders and compared the period. We had 3 trials and averaged the data. As you see here, the red and the orange lines represent the mathematical data or the mathematical percent change we should see from the vehicle itself. Here at the vertices, the vehicle will be traveling straight. So both wheels, inner and outer, will be traveling the same speed. The wavy lines are what we actually measured from the wheel encoders themselves. Now, if you see here, this variation can be contributed or attributed to friction and also electric motor variation, battery discharge, and other elements that you see in a realized product.
In terms of administration, we spent roughly $600 on components for this project. Most of our original components were utilized in the final project. However, some of the original RPM sensors we had to replace, and we originally started with 4 motors that did not have enough torque to power our car. In total, we spent 440.5 hours of design and testing on this project this semester. If you posit that an entry-level electrical engineer would be paid $20 an hour, the total cost of our project for parts and labor would be $9,407.07. Lessons learned from this project. We learned quite a few lessons from this project. First of all, clearly define your project and don't work too much on extraneous features. That leads us directly to our second point, which is make the mechanical engineering aspect simple. One of the problems we encountered in this project is that we're not mechanical engineers, and we spent a lot of time working on the steering components of this project. Our third lesson learned is don't count on a sponsor to be reliable. In the first semester of our project, we had a sponsor who was originally offering to do the mechanical fabrication of our project, but he disappeared early in the first semester. Another important thing is to turn your research time into productive time. Our original strategy was divide and conquer, as in everybody work on their individual components and then come back and collate our data. This didn't work for us very well, and we ended up choosing to work as a group, which made it easier to pool our resources and time. Another lesson learned would be that if you plan to use microcontrollers, and most projects use microcontrollers, make sure that at least one person is taking ECE 447. ECE 448 helps a lot too. So if you're planning to take senior design, or this is only your first semester, we would strongly encourage that. Another important lesson learned is be ready to have no life for the duration of your senior project. If you think you're spending time with your loved ones, your family, and your friends, you're not. You're spending them with your senior project members. And our last lesson learned is more of a group harmony lesson, which is that if you keep your group happy, it's easier to get along. Our solution was donuts. The sugar rush kept us motivated, and as a side note, Dunkin' Donuts is right across the street. Every team member worked on this project, and we all did various roles. Our defined roles were that I was the project manager, Jen Heindel was the technical manager, Ben Gazlay was our chief programmer, Marc Edgerly was in charge of component acquisition and funds management, and Johanna Arias was our data manager and was in charge of documenting the circuit schematic. We have a short video for you. We apologize for the silence. There's some music and some other groups made it really interesting. As you can see, this is us powering our wheels. This is as the test platform was continuing. This is car being controlled straight, car being turned. And lastly, this is the testing. As you may be able to see from this picture, the oscilloscope triggers on one encoder only. So as we increase the steering angle, one wheel encoder is going faster than the other. We would like to send our thanks to our faculty supervisor, Dr. Packowitz. We would also like to thank Dr. Cook for his help on theoretical equations, and Dr. Beatty for materials, advice, and in terms of robotics. Do you have any questions?